Okay, so just like in section 7.1, I need to preface this video by saying that I have some work being done in my house right now, and you might be hearing some banging and scraping and whatever in the background. Hopefully it's not too distracting, but that's what that is. So in 7.2, we're going to be talking about the inverse Laplace transform. And the name of this implies a property of the Laplace transform that we're not going to prove, but is important. And that's that the Laplace transform is invertible. It's one-to-one, provided that we're taking the Laplace transform of continuous functions on the restriction that we place on S. So basically, we're not proving that, but we're going to be using that result. So basically the goal here is, remember, when we take a Laplace transform, this should say L of f of t. What we're doing is we're taking a function of some variable t, plugging it into that transform, and out pops a function of a variable s. Now we're ultimately going to be using this to solve differential equations. And in the differential equations, our solution to the differential equation that we're trying to work out is going to be a function of t. And so what we're doing is we're taking that function of t and then creating a function of s out of it using this Laplace transform. But our solution to that dE cannot be a function of s. So we need some way of getting from that function of s back to a function of t again. And that's what the inverse transform is going to do. So the way that we define this is the same way you would define any inverse function. But if you have a function f of t and its Laplace transform is capital F of s, then the inverse Laplace transform of that capital F of s should take you back to that lowercase f of t. And from that definition right away, we can find a bunch of inverse Laplace transforms of particular functions by using what we did in the previous section. So if you're seeing this and you're saying, where are all these coming from? If we go back to section 7.1 and we look at that table of Laplace transforms that we came up with, simply taking each one of these and taking the inverse Laplace transform of both sides will produce this table. So like, for example, notice the Laplace transform of t to the n is equal to n factorial over s to the n plus 1. That would mean that t to the n equals the inverse Laplace transform of n factorial over s to the n plus 1 power, and the rest of these are derived in a similar way. Okay? So this property, or this, sorry, not property, but this definition allows us to come up with this table, and these are very specific looking functions, like for example n factorial over s to the n plus 1 power. How do you evaluate the inverse Laplace transform of functions that look kind of like these functions but may not match exactly? Well, in this case we need to use the linearity property once again, and I actually state it down here. And again, we're not proving this, but there is an important property from linear algebra, which is that if you have a linear transform, or linear transformation, as we call it in that class, and it's one-to-one, and we would say onto in that case, then its inverse is also linear. So the fact that the Laplace transform is a linear function implies that the inverse Laplace transform is also linear. And so we have this property. And this, again, remember, this allows us to split this up into a sum of inverse transforms, and we can pull constants out. So how are we going to do this example? We want to evaluate the inverse Laplace transform. Let me zoom in a little bit. Of 1 over s to the 4th. Now, using my table up here for reference, this Laplace transform most closely resembles this one, because this is the only one where there is an s to a power in the denominator and nothing else. So the issue, though, is in our example, s to the 4th would imply that this n here is a 3. 3 plus 1 gives me 4. But if that's the case, then I should be seeing a 3 factorial in my numerator, and I'm not seeing that. So here's what we do. This will equal the Laplace transform of, remember, we want a 3 factorial showing up there. s to the, let's write this as the 3 plus 1 power. Okay? If I multiply the outside of this Laplace transform by 1 over 3 factorial, and then use the fact that I can pull this constant out, that's my linearity property, which we state down here, I can pull that out and cancel it, and I would get back to this, okay? So by using that linearity property, we were able to put this thing in a form that matches something that we already know the inverse transform of. 1 over 3 factorial is 1/6. And this Laplace transform, n in this case, is 3. And this would equal t to the 3rd power then. Okay? Notice I didn't have to do any integration or anything like that. I just use what I can from the table along with my linearity property. Let's try another one. So in this case, the function looks a little bit more complicated, but notice my denominator looks like s squared plus 2. Now that, if I just focus on the denominator, resembles d and e. Both of the denominators have s squared plus something else squared in it. So the problem, though, is the numerator only has a constant here and only has an s here. I have both of those things appearing in my numerator here. So in this case, I want to use my linearity property again, but it's to split this up into a sum. So now we're looking at this. The inverse Laplace transform of s over s squared plus 2 plus the inverse Laplace transform of 1 over s squared plus 2. Now this guy, this s over s squared plus 2 most closely resembles this one, s over s squared plus k squared. In this case, k squared would be 2, which implies k would be the square root of 2. So this comes out, using that table up there, to cosine of the square root of 2t. All right. Now my second one, again, looks like this guy. I have a constant in my numerator, right? The problem is the constant's not looking like what it's supposed to look like. I'm supposed to have a k up here, where that k comes from this k squared down here. Once again, my k squared is still 2, so k should be equal to root 2. And I can make that happen using the same trick as the last example. Multiply this by 1 over root 2, and then put a root 2 up here, s squared plus 2. And then this becomes cosine of root 2 over t. Oh, sorry, of root 2t. Move that up. Plus 1 over root 2. And this one, according to my table, would be sine of root 2t. Okay? I'm going to have to cut this video short. We'll pick up where we left off in the next one.